Okay, guys, if Vanessa didn't find me here, you guys, I was never gonna do this. And then, anyway, yeah, that doesn't matter. So I'm gonna try to do this with my computer, and it's really hard because this is gonna be kind of hard to use. So this is what you have is a circuit, right? And you need to find all these values over there. God damn it! You see what I told you? What I told you? It's gonna be a little bit hard. Erase all ink. All right, good. Now you gotta find all those values up there. Okay. So what I'm gonna do first is I'm gonna start by separating the circuit. The reason I'm doing that is so that you can understand exactly how this bullshit works. You guys know that I don't like cramming stuff. I like separating things. Okay, so there we go. I'm gonna analyze the circuit individually, just like that. Okay. If you understand the impact of every circuit, of every part of the circuit in the whole thing, you'll understand the whole bullshit. So I'm gonna start by separating like this, and I'm gonna call this side 1, and this other side I'm gonna call it 2. Okay, so you're gonna start with 1 first, and then we're gonna go with 2 after that. And then we need, since all of them are combined, then we're gonna combine and see how they come together. Okay, good shit. User saving. Okay, now over here, where's the bullshit? No, not this one. Where's this thing? This one. All right, so now this is the first one. This is the second one. Okay, so over here, you see this is the first thing, the first circuit, as I tried to draw it as clear as possible. This should be clear enough, right? Yeah, this should be clear enough. So must I zoom? Nope, 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 nope. Okay. All right, this is the whole thing. Now, before I do anything right now, you guys need to understand exactly how the whole transistor thing works. We've got a transistor here like this, right? We know that for this transistor to conduct, I mean the current to go from the collector towards the emitter. Pay attention to my words. For the current to go from the collector to the emitter, meaning it's conducting, there must be for it to conduct. God damn it! What am I doing? Okay, this is what we've got. For the transistor to conduct like this, there must be some type of voltage over here and there. There must be voltage on both sides. Guys, 0 is also a voltage. And notice that I didn't put a ground here or anything. Now, on the base, the voltage on the base must be higher than the voltage at the emitter by 0.7. So there must be a difference of 0.7 between the two. Alright, which means if I have, let me erase all the ink. If I have 10 volts here, your right mind, okay, let me not write there. Let me just redraw my transistor here. Okay, so if I have 10 volts here, here should have 9,3. If I have 5 volt here, I should have 4,3. If I have 0 volt on the base, I should have minus 0,7 on the emitter at this point for this transistor to conduct like this, for it to conduct, alright, and the current also go like this. Okay, so you get me? So if I have minus 2 volt here, the difference between this and that must be 0.7. Therefore, if I have minus 2 volt here, it must be minus 2,7. Do you see that? Because this is not big, this is bigger than that by 2.7 volt. Do you get that? Once you understand this, you're good to go. Once you do this is something that all of you know, so I'm sorry for wasting your time. But either way, now let's analyze this part here. Over here, we've got ground, right? Which is 0 volt, isn't it? Oh, before I even go there, let me draw something quickly. We know that a transistor acts like a switch, isn't it? So I'm gonna do, let's say this is a switch and it's open, right? This switch is open. So over here, this is a transistor. This empty space here, transistor Q1, okay? And this is my plus 20, and this is my minus 20, okay? Now, the transistor is not conducting yet, meaning the voltage here is not higher than the voltage there by 0.7. Let's just assume for now it's not conducting, okay? Now, if I ask you to measure the voltage at this point with respect to ground, what are you gonna measure? What are you gonna see? Remember, ground is 0 volt. If I had to put one probe here of a multimeter at this point and the other probe on ground, wouldn't you just see, let me show you, wouldn't you just see this part like this on top here? Like that? Since there's no, it's open here, there's no current flow, so the voltage at this point and the voltage at that point will be exactly the same. So here you're gonna see plus 20 volt too at this point because there's no current flow this way. All right, so it's like, since there's no current flow here, this resistor doesn't have any more value. It's like a wire now. Therefore, there's gonna be like a direct connection from there to there. Okay, because no current is going through here. It's like an open. Over here as well, if I had to measure at this point, you're going to see minus 20 volt. Why? Because this point, because there's no current flow this way, it is directly linked to minus 20 volt. Do you see that? Yes, you do. Now, as soon as I, let me go to, let me not go to some gay color. Let's go blue. Now, as soon as the transistor starts conducting, I switch on the transistor. Now, this part is connected. Hold on. I need something thicker. I need something thicker. As soon as the transistor starts conducting, there's, what the fuck? What is this? Hello? This part will be closed, isn't it? Alright. Now, what we're gonna have, let me remove all this. Now, what we're gonna have is plus 20 volt here, some resistor there, minus 20 volt. You see, now it's like this is where the transistor is. Now the transistor is conducting, isn't it? Now at this point we've got now different voltages. Now there's going to be a voltage divider over there, you see. But if for some reason this spot here was open like this, when the transistor is not conducting, which means there's an open here, okay, here you're going to see plus 20 volt, here you're going to see minus 20 volt. Get that into your mind. I'm not going to be at school tomorrow morning. I need to attend something and I'm going to be there only later. So that's why I have to I'm recording this, and also because of Snow kept on asking record, you know. So yeah, she likes taking videos, that one. Anyway, so yeah, now we understand this part, isn't it? Good. Now I'm gonna remove all the ink again. Now we're back to this thing. Okay, so currently, let's say currently the transistor is not working, all right, which means this point here is open, isn't it? Right, there's no current flow here, and there's no like this, and there's no current flow like that, isn't it? Which means at this point here I'm reading 20 volt, and that I'm gonna read minus 20 volt. Do you see? Now let's apply some base voltage. Now I put 0 volt here, okay? As soon as I apply 0 volt there, now you gotta ask yourself, does the voltage at the base, is the voltage at the base bigger than that one? Yes, if it's bigger, that means it will allow current flow to go like this. Remember, current flows from bigger voltage to smaller voltage, okay? Current flows from higher voltage, higher potential, to smaller potential. Remember that, you know that. All right, so since there is a minus 20 here, therefore current will be forced to go in this direction, isn't it? And because the transistor is not conducting yet, this minus 20 will appear there. Now, we bias the transistor, okay? As soon as we bias the transistor, suddenly this transistor turns on, isn't it? Now, there's no more minus 20 here, right? Now, the minus 20 is over there, like we see there, okay? That minus 20 here was an assumption that the transistor was off, so we had to see how the current direction will go. So right now, we know that minus 20 is there, smaller voltage, bigger voltage, current should go this direction, isn't it? Good. Now, the fact that 0 volt here is bigger than whatever voltage that is that side, alright, meaning the transistor should conduct, isn't it? Now, remember that we don't know exactly how much voltage is here right now. We know just there it's going to be minus 20. But we know that if the transistor is not conducting, this minus 20 will appear also there. When it starts conducting, it's a different story. Okay, keep this in mind. When the transistor starts conducting, the voltage here and the voltage there are different. When the transistor stops, is not conducting, is off, meaning there's an open circuit here, there's no current flow anyway, this voltage will appear over there. Okay, it's like this resistor is not even there, it's like a straight line, a wire, a piece of wire. Do you understand that? Repeat this, pause, go back if you need to. Alright, now over here, now the transistor starts conducting now because it's 0 here. Remember, for it to conduct, it has to be 0.7 low. This must be 0.7 higher than that. So if it's 0 here, here it must be 0.7 volt, isn't it? And that way, we have current flowing from the collector down to the emitter, isn't it? Now we know that at this point, since here is 0, and this must be higher than that by 0.7, I forgot that, negative, we know that it's going to be higher by 0.7. We now know the emitter at this point, it is 0.7 volt. Okay, therefore, this first part of the circuit, we know now at this point we have 0.7 volt. If we have 0.7 volt here, because there's a direct connection over here, it's also 0.7 volt, of course. This should be obvious to you guys. Minus 0.7, I mean minus 0.7. Fuck, I keep on forgetting this minus. Fuck, why did I show you that? Anywho. Okay. Now, we know that it's 0.7 minus 0.7 volt over there, right? Now, since we know that 0.7 volt at this point, they're going to, your questions, one of them, if I bring up, hold on, if I bring up this thing of yours, do you see that one of them is asking you VRE, okay, VRE. So VRE is this voltage across RE, and you guys know that voltage across a resistor is voltage on one side minus the voltage on the other side, so it's going to be minus 0.7 plus 20. Why 20? Because it's going to be 0 plus, why plus 20 is going to be minus 0.7 minus 20. You see, minus 20 is this one over here. Okay, do you see that? So voltage across the resistor is going to be voltage over here minus voltage over there. So now that we've got this voltage, which is going to be what? 19.3 over here. Now we have the voltage there, we divide by this, we get the current over here, isn't it? And since you have the current over here, and you can assume that IB equals to IC. You guys know that you can make that assumption. Therefore, the current here will be the same as the current over there. And Ohm's law again gives you the voltage over there. Alright? Good shit. And you will see that I'm not going to use any of those funny formulas of yours. Okay? Now this is only for the first part of the circuit. Key word is understand where the 0.7 volt here comes from. Okay? Keep that in mind. Holy fuck. Actually, I want to replace this. Okay. Yes. No, are you fucking kidding me? It's my own image. Anyway, let me just save a copy of it. Okay. Letting your ink dry. Good shit. Okay. Now, this is the second part of the circuit. The first one has... Okay, that's cool. The second part now has the side. The same bullshit. Oh, I forgot to put the ground here. But you know that when I say minus 15, it's with respect to ground. So I'm gonna ignore that. I'm gonna say minus 0.7 here. And the approach is exactly the same. So first you assume that you know that the transistor is not, this is not applied there. So we know that it's minus 20 volts over here, isn't it? So it's gonna be minus 20 volt over here. Okay. Now, minus 15 is higher than minus 20. Therefore, current will flow this way. Okay. Minus 15 is higher than minus 20. Current will flow in that direction as soon as the transistor turns on. Now, because minus 15 is bigger than that, the transistor will definitely turn on. Guys, remember here I'm analyzing these things individually. I'm not putting them together. On this side, this individual part of the circuit should work on it. If it worked on its own, this is basically how it would operate. Okay. I haven't put them together yet. So on this side, it would conduct like that, isn't it? So now we apply the minus 15 and we have minus 20 here. We know that this is bigger than that, so current should go in this fashion. Okay. Now that we are sure of that, current will go in this fashion. Let's see how much voltage is going to be there. Now, for this current to go this way, for the transistor to turn on, the voltage here must be higher than the voltage there by 0.7. So if this is minus 15 over here, to make it's going to be minus 15.7. All right, so that if I take this, I subtract that, I'm going to get 0.7 over here. Remember, it's a diode. It's a fucking diode. The difference must be 0.7. You guys know that. Okay, so now at this point, we know that here I must get minus 15.7 volt. Okay, now if I have minus 15.7 here and after minus 20, I subtract this to that, I get the voltage across that resistor. And this is 2K, of course. Across that resistor, Ohm's law, I get the current. I assume IB equals to IC. Ohm's law again, I get the voltage over there because I know the current there. Do you see that? Easy, isn't it? Just like that. So I'm going to say erase all ink. Now I'm going to say minus 15.7 volt here. Again, save. Good shit. Now we've got both parts. Now let's mix them together. Here is what we have. Focus on this side first. This side. Okay. Now when I put them together here, on the previous image you saw that, notice that here I put the like this, and over there I put dashed lines. Okay. Kind of to separate them, but we know that they must connect, isn't it? Now, here's the thing, guys. We know that over here I had 0.7 on this side. Here I had minus, oh no, I had minus 0.7. And here I had minus 15.7. Okay. Now all of these meet over there. We know that this is higher than that one. Okay, this is higher than that one. But all of them meet over there. Now, at this point here, with respect to ground, which voltage here would appear? Is it going to be 0.7? Is it going to be minus 15.7? Is it going to be the sum, or is it going to be the difference of the two? Well, to prove this to Vanessa, I ran a quick experiment with her, and if you are interested in knowing what I just did, you can ask me whenever you see me. But I can tell you that here at this point, because here we've got minus 0.7, here we got minus 15.7 at this point, and that over there, because they both meet over there. Over here you're gonna get the highest of the, god damn it, the highest of the two, which is gonna be minus 0.7 volt. Do you see that? The highest of the two. So first, over here I had I had something like this, and then we found out that 0.7 volt appears over there. All right, we need 0.7 volts. It's actually not 0.7 volt, it's minus. Guys, I keep doing this. Can you guys let me do this? This is your fault. What am I doing? Cancel. Edit. No! I'm a potato. Draw. Yeah, it's minus. No! That one. Minus 0.7. Good. I'm a Please don't tell me I don't have permission. God damn it. Okay, I'm gonna resave it differently. Okay, now we saw that first we had this, and then by applying all those funny bullshit, we've got minus 0.7 volt over here. Okay, and secondly we had this part, and we found out that over there it's going to be minus 15 volt. Now because they have both to meet, uh, at this point, minus 0.7 minus 15, god damn it, 0.7 minus 15.7 over there is going to appear minus 0.7. So it's going to ignore this. Why? Because this is higher than that. So this is the one that's going to have influence over this point here. Alright, and this is very critical. The bigger voltage will influence the point even if you put them together. You can try that. You can take two different power supplies of different voltages, connect the grounds together and connect the positive together, and when you measure, you will see that you'll measure the positive, the higher voltage. Okay, so over here we're going to have 0.7 because this is too small to influence 0.7. All right, so if I remove all that, erase all in, now we know that over here we're going to get minus 0.7. Okay, good. Now I'm going to close that gap like that. Okay, now we know that this is 0.7 volts. Okay, this is RC2, of course, don't have to tell you that, and this is RE. Okay, now we're gonna have 0.7, which means this minus 0.7 appears here, and this other minus 0.7 appears here. Okay, fuck the minus 15, something that I showed you before that we found, because that one was just meant to show you exactly on this side of the circuit individually how it would have worked if it was on its own. All right, but because it is connected to this other side, this will have influence over this side. Okay, this will influence this side, and you see it over there. You see this voltage here that is connected to this one over there is going to take over because it's bigger. All right, good. Now we got minus 0.7 over there. Okay, now we know that is minus 0.7 here and minus 0.7 there. Okay, but here we know we have minus 15, minus 15.0. Okay, it's just minus 15. I was about to make a mistake. So minus 15. So here we've got 0. We know that over here we also have minus 0.7. Okay, so we know that this transistor is conducting definitely. Okay, but check this out, because this is influencing over there. Now this point has minus 0.7, isn't it? Here we have minus 15 and minus 0.7. It's now known. We have a minus 0.7 now. Now because of this minus 15 and minus 0.7, this voltage is higher than that. And remember, the current flows from bigger to small. Current cannot go this way because this is a diode. It has to come this way only. Alright, current cannot go this direction, you see. So therefore, this part does not conduct at all. Okay, this is satisfying. I'm enjoying this. This part does not conduct at all. So this transistor is not even there. Assume as if it wasn't there. Okay, that brings us to the side of the circuit. Okay, that's why minus 0.7 there, minus 0.7 here. I keep on writing this so that I don't confuse the stupid ones. Okay, I didn't say anybody is stupid. I'm sorry. So minus 0.7 over here. Remember what I started explaining? Now that the transistor is not there, now it's open over here, isn't it? This is open. So current is not gonna go through there because it's open. Now because it's open, over here we're gonna have minus 0.7 because that's where it's connected to. Over there we're gonna have plus 20 volts on the collector. Do you see? Do you see that? Do you see that? The only part now that's gonna influence the current going there it's gonna be the side. Okay, because this transistor there is not there. Now we know it's minus 0.7 here, minus 20. The difference gives you 19.3 volts RE. This one minus that one gives you 20.7 for VCE. 20.7 because we have collector here minus plus 20, emitter there minus 0.7, you see. So if we have plus 20 here, plus 20 there, what is VRC2? It's going to be 0 volt. And it makes sense because if this is open, no current is going to flow there. If there's no current through a resistor, there shouldn't be a voltage on it. Doesn't it make sense? And that's how you solve this bullshit. You see? Over here, it's going to be the same thing. We have a 19 comma something. We do Ohm's law. We find the current. That's going to be, if I take 19. Where's my calculator? If I take 19.3 divided by, what the fuck am I writing? 19.3 divided by 2k, 2000. You see, 9.65 milliamp. So you're gonna get 9.6 milliamp here. Now, since we can assume that the current here and the current there is the same, so over there we're also gonna get 9.6 milliamp. Okay. Over there, through a 2k, the voltage here is gonna be the same as the voltage there. And there you go. Now we can find the voltage here. You can find the voltage here. You subtract to get your V out. Easy, isn't it? That looks like a kid's drawing. That was 27 minutes of video. And just by this, you guys owe me 50 bucks each. Just know that. And I don't ever want to hear anybody say, no, I don't care about you guys. Or ever say I'm moody for no fucking reason. Okay? Good. Bye. See you next time.